so I've got an exciting announcement to share with everyone. Hopefully you were able to attend the poster session last night before dinner, or if you didn't, you were able to at least browse through some of the amazing work that our students were demonstrating and presenting out to the members here that are joining us. And so what I wanted to take a minute here just to give maybe a quick round of applause to all the students who entered a poster and were sharing their research with us. So. You know, I was telling some of my colleagues, normally I have to go to a conference to learn what my colleagues are doing, and here I had the opportunity to not travel and still get that great conference experience of seeing what all my great colleagues and their amazing students are accomplishing here. So without ado, I want to announce now the winners for this poster competition. So we had a couple of 3- and 4-way ties. So if you see your name here come up, please, students line up. We'll do the bronze, silver, and then gold, and come up and get your certificate. So, all right. Jinrong Su. Priyanka Vishwanathan. And Maxwell Woody. Thanks. All right. All right, and Alan is reminding me we do have prizes for the winners, so that's more motivation to come up and share. All right, next up we have our silver award winners. So we've got Yimin Zhao. Woo Jun Suk. All right. All right, and Miki Tsusasha, hopefully I'm not butchering anyone's name. Suchiya. All right, thank you, Alan. All right. All right, and we have a 4-way tie here for our gold winners. And so if our gold winners can come up, we're gonna also have them give a quick lightning talk, so a 5-minute overview of their poster. So first up, we have Elliot Busta. All right. All right, yeah, so we'll do pictures and then have you guys up for a talk. Great. All right. Actually, we could have you have some. No, I'm just kidding. All right. Kishan Sirvasan. All right. We have Jordan Perks. All right, and finally, Shravan Panala.
Hi, everybody. I'm Elliot Busta. I am a master's student studying energy systems engineering, and I work in Gregory Keolian's group doing life cycle analysis on electric vehicle lithium-ion batteries. I see. Click this. Great. So specifically within the life cycle analysis of electric vehicle lithium-ion batteries, this research was looking at environmental trade-offs between NMC, or nickel manganese cobalt, and LFP, or lithium iron phosphate batteries. So we know that electric vehicles are more sustainable than internal combustion engine vehicles, but we still want to manage them intentionally to maximize the benefit that they can provide. So our project objective is to kind of look at the trade-offs, environmental trade-offs between these two chemistries, which are the most popular chemistries, or two of the most popular chemistries in electric vehicles today. Quick overview of life cycle analysis for people who may not be familiar with it. So it looks at from the mining and refining stages, manufacturing, use, and then into kind of end of life, which hopefully has some circularity aspect to it. So we're looking at, when you stack all of those things together, what does that mean in terms of the environmental impact? We use Argonne National Lab's Excel-based GREET model to simulate these. And here are a couple of key parameters that kind of drive the conclusions that I'll show in this next slide. So preliminary results in terms of greenhouse gases, you can see on your right, I've got at the top a chart showing the different chemistries across the bottom. So LFP and then different atomic ratios of NMC. And the first thing that we notice is that LFP has lower vehicle cycles. This is the various manufacturing, mining, and refining stages impacts, but it has higher use phase cycles, higher use phase impact. And the reason for that is because while LFP has lower emissions in the mining and refining stages, it's a less energy dense material. So you need to manufacture more of it, and then you need to cart around more of it when you're driving your car, which leads to lower vehicle efficiency. The other thing that we found is that as you increase the nickel content in your battery, you actually get improved sustainability. And this was a bit of a surprising finding for us because nickel mining and refining is a emissive process. And so you would expect that as you increase the thing that has a lot of emissions, you don't get a more sustainable process. But what's actually happening is as you increase the nickel content, you get higher energy density, and that leads to producing less material and moving around less material. And so with moving around less material and producing less material, that overwhelms the emissions aspect of the nickel mining and refining. The other thing that we looked at is recycling for these various chemistries and for a couple of types of recycling. So I think my legend got cut off there, but these are virgin in blue, hydrothermal recycling in yellow, pyrometallurgical in gray, and then direct recycling in light blue. And so what we find is that implementing recycling improves the sustainability across these different methods and chemistries. And then another thing that you can see is that LFP recycling provides a lesser benefit. And this is because we aren't avoiding the emissive nature of nickel mining and refining. Whereas with the NMC chemistries, you are avoiding those. So that's a benefit of that mining or a benefit of implementing recycling there. If you guys are interested in learning more, happy to discuss it further. And we can walk over and check out a little more information that I have on my poster. But thank you so much, and thank you, EV Center, for giving me this award.
Before I start, I would like to thank the EVC team for giving me the opportunity to talk about my research. And most importantly, I'd like to express my sincere gratitude to my advisors, Professor Heath Hoffman and Professor Sun, for the guidance and support in doing this research. So the topic of my talk is accurate nonlinear magnetics model for permanent magnet synchronous machines for a real-time control application. The objective of this project is to come up with a nonlinear magnetics model for permanent magnet synchronous machine, aiming for a real-time control application, so that more so in capturing the nonlinear behavior due to magnetic saturation and temperature variation of the permanent magnet on the rotor. The main contribution of this model is the decoupling of the magnetic saturation and rotor temperature variation. Looking at the proposed model itself, looking at the simplified single coil permanent magnet simplified block diagram, the conventional way to model a permanent magnet is to model it as a flux linkage source, which varies with its temperature. What happens when you model a permanent magnet as a flux linkage source is that for a change in rotor temperature, you get a constant offset in flux linkage. But when you look at the actual nonlinear flux linkage current mapping relationship, especially in the nonlinear region, when you experience saturation for a change in rotor temperature, the offset is no longer constant in flux linkage. So what we propose is trying to model the permanent magnet as a bounded current source, which is again a function of rotor temperature. And what our proposed model predicts is for a change in rotor temperature, there's a constant offset in current, and that's what we observe when we look at the nonlinear current flux linkage relationship. There's actually a constant offset in current. That's what the proposed model predicts. Another main contribution of the proposed model is there are two components to the proposed model. One is what we call as the nonlinear current flux mapping, which is independent of the rotor temperature, so just captures the saturation behavior. And then you have the permanent magnet parameter, which is solely dependent on the rotor temperature. So we're kind of able to establish a decoupling feature between the saturation and the rotor temperature in the flux linkage current relationship. This helps us to have an accurate adaptive estimation of the permanent magnet excitation without additional use of sensors. So an example implementation is what I've shown here on the bottom right figure to illustrate the computationally inexpensive of this model. When you want to implement like a flux linkage to current mapping, you have a two-dimensional lookup table, which is the current flux linkage mapping in our proposed model, which is once you characterize the machine, it becomes a constant that captures the saturation behavior. And then you can have an adaptive estimation technique to estimate the permanent magnet current. So in terms of validation, we kind of validate the proposed model both in simulation and experimental results. In simulation, we simulate an IPM inter-permanent magnet machine using ANSYS and try to show how the conventional model, which models a permanent magnet as a flux linkage source, predicts the torque and how our proposed model predicts the torque. And what we see on the plot on right, especially when you are experiencing deep saturation, when you have high torque, high IQ current commands, and for a wider temperature, rotor temperature variation, the conventional model has a higher degree of error in terms of predicting the torque, whereas our model is able to accurately predict the torque, and that is primarily because of this decoupling feature of saturation and rotor temperature variation. We also have experimental validation, kind of show the same accuracy of the proposed model as compared to the conventional model in literature. The future work is taking this model and using it to come up with an accurate high-performance torque regulator. So I have a sample flowchart, block diagram of the proposed controller. So the proposed model will be leveraged to be used in having an accurate torque to current mapping, reference commands, adaptive estimation of the permanent magnet, and also building a accurate flux observer. And that, I think, time's up. Thank you so much.
Good afternoon, everyone. My name is Jordan Perks. I am a PhD candidate here at the University of Michigan in the School of Electrical and Computer Engineering. My faculty advisor is Professor Heath Hoffman, and my research is the high-performance current regulation of SMPM machines using FPGA-based field-oriented control. So I guess to unpack the title a little bit, surface mount permanent magnet machines, or SMPM machines, are very frequently used for automotive traction in electric vehicle applications. In general, the control objective for these types of machines is the regulation of torque, but this is often achieved indirectly through the control and regulation of currents. Now, the problem that we're trying to solve is that in conventional microprocessor-based control applications, we see a significant introduction of calculation delay. And this calculation delay has a very negative influence on controller performance. And so to try to understand where this calculation delay comes from, we have this figure here on the top right. This is showing the typical microprocessor-based control calculation timing. So in general, when we are supplying power to a SMPM machine, we are doing so with an electric drive, and we're utilizing pulse width modulation to supply the voltages and currents that the machine requires. And so in essence, the sort of ultimate control objective is the calculation of a duty cycle to control that pulse width. And when it comes to the actual sort of sequence of events, what typically happens is we sample the current, we perform all of the control calculations necessary to determine the duty cycle, and then we apply that duty cycle. But in conventional microprocessor-based applications, the calculation time ends up being quite substantial. And by the time you're able to actually apply that duty cycle calculation, enough time has passed that you're actually using data collected from the previous steps sampled data. And so this ultimately ends up in at least one sample period of calculation delay. And so the objective of this work is to implement a controller on an FPGA, field programmable gate array, to perform many fixed point control calculations in parallel in order to accelerate the speed at which we can compute the duty cycle. And so the figure on the bottom right is showing typical FPGA-based control calculation timing. And the idea here is we want to shrink that calculation time as much as possible. And if we can get the calculation completed before we issue the duty cycle pulse, the hope is that we can implement that duty cycle in the same switching period that it is sampled and in essence eliminate that calculation delay. But there's one minor catch here, and that is that we have to be able to perform this calculation before that duty cycle pulse is issued. And this necessarily leads to a restriction on the range of duty cycles that we can utilize. And so in order to practically implement this, we need to reduce that duty cycle limitation as much as possible by reducing the calculation time as much as possible. And so the proposed controller on the top left is sort of a typical field-oriented control of an SMPM machine that we've modified in order to accelerate the calculation time. And so it consists of a disturbance rejection and integral control term, sort of shown in this slow calculations block, and a proportional and state feedback term shown in this fast calculation block. The idea is if we can implement the calculations that take the fewest amount of time to compute, and we can implement them quickly and issue that duty cycle command, then we can eliminate delay as much as possible. And the slow calculations, we can allow them to be delayed. And the idea is that we can use delayed information with them combined with the fast calculations, so that way we're not holding up the entire controller on the slow calculations. And when we implement the controller in this way, the figure on the right shows a step response of the current. You can see that the conventional delayed controller has significant performance issues with overshoot, settling time, and cross-coupling issues. But not only that, it shows the ideal regulator in green and the proposed regulator in blue, and you can see that they are almost right on top of each other. So the conclusion here is that the proposed controller is able to achieve very comparable performance to the ideal undelayed regulator, and it's doing so while minimizing the calculation time as much as possible. In this case, we were able to achieve a calculation time using the hardware in our lab of 248 nanoseconds, and that corresponds to a duty cycle limitation of 99.5%. So with that, that concludes my presentation. Thank you for your time.
Hello everyone, I'm Shravan Panala. I recently defended my thesis 2 months ago, and my advisors are Jason Siegel and Anna Stefanopoulou. So my PhD work and also this poster presentation is about tuning physics-based models for predicting battery lifetime degradation. Am I audible? Sure. Okay, so we all know that batteries degrade, and here is an example of the data we collect to study how batteries degrade. So we have current, voltage, and displacement. So on the right, you can see a voltage profile of a fresh or undegraded cell and a degraded cell. So we see that the voltage profile change. Why does it change? It's because there are electrical changes in the battery which happen as a degrade, which include changes to both the battery's capacity and also resistance. That leads to changes in observed electrical behavior. In addition to that, batteries also have mechanical changes. So what are mechanical changes? Batteries are just like humans. So when we breathe in, they expand. Again, we breathe out, we contract. It's the same thing. So when you charge, they expand. When you discharge, they contract. And in addition to that, as they age, they irreversibly grow. Again, just like humans, as we age, we irreversibly grow. It's the exact same thing. So yeah, there are a lot of similarities between batteries and humans. So we want to understand how these batteries change and actually predict, okay, when do they die? So yeah, so the approach we took is taking physics-based degradation models to connect these degradation mechanisms which happen in the battery to these observed changes. And also we want to tune these models using the degradation data we have collected by doing lots of experiments, as you can see in the experimental fixture seen there. Yeah, so I won't go into details about our model. You can come to my poster or read the paper. The citation is here, but I want to just say what our model do and how does it do. So what can our model do? It can predict, as I said, like capacity loss and resistance growth. So why do you want both? Only if we can predict capacity and resistance, we can predict the voltage profile. As you can see on the top left, we have two voltage profiles, one at beginning of life, another at end of life. So if our model is able to capture both resistance and capacity, we are able to predict the voltage profile with good accuracy. And then we go to reversible expansion within a cycle and irreversible expansion between fresh cell and end of life. So if you are able to capture that, we can predict total battery thickness throughout the life. So how do we do it? So we do it by considering these three degradation mechanisms and link them to observed changes. The first one is SEI growth, which we link to loss of lithium, resistance growth, and also irreversible thickness changes. Lithium plating, again, the same thing, loss of lithium, resistance, and irreversible thickness growth. And finally, we have mechanical damage or particle cracking, which we link to loss of active material, resistance growth, and also irreversible expansion. So one good thing about this model is like we have taken 6 cells at room temperature, and just one set of parameters can capture a wide variety of cycling conditions, including different C rates, different depth of discharge, and different like charge and discharge conditions. Yeah, so how does it work? So we have model, we have data, so we have to connect both of them. So how we do is first we define a set of vector of degradation mechanism parameters. I've shown you what the mechanisms are. So we consider a set, depending on the data, what we want to use, we tune a subset of them. And then we define the data to be fitted against the model. This can include normal observed changes like capacity and resistance expansion, but also what we term as electrode state of health, which gives more insight into the degradation modes. And then we run least squares optimization, which we enable using accelerated aging simulations, and then finally we get estimated degradation mechanism parameters. So our model can predict aging under conditions not used for tuning. Again, that's an advantage of being a physics-based model. Thank you for giving me the opportunity to speak. And if you have any questions, you can come to the poster, talk to me. Thank you.